Good, okay. All right, so what we're gonna do today, we've been kind of in this mode of wrapping up the last lecture slides and then getting into new stuff. So we'll continue with that. But just wrap up the problem that we started last time, which is our extended surfaces problem for this ringed fin. We'll finish up this problem, and then we're gonna start talking today about 2D problems, 2D conduction, which is kind of interesting and something new that we really didn't get into a lot in 364. Okay, so where did we leave off? We left off last time with this really messy chart here where we say we're trying to go through and we identify a function. We identified a function that looks something like this Bessel equation. Okay, this is Bessel's equation. This over here was our function that we got as our governing ODE. Right? This is our function of temperature that we need to solve. And it has a differential. The thing that makes it a Bessel's function instead of just something we've done before is, right, you have R in here and we have R times T over here. So that's kind of what makes it a Bessel's function. So we identify it as a Bessel's function. We then go through this just matching, pattern matching. We say, okay, P corresponds to, in our case, what, 1, and S corresponds to, in our case, 1, C is M, or you can just kind of go through and match things out. We've done that here. Once you do that, then you just follow this chart. So for our case, we're going this way, and we end up following this path over here. Okay, so this path, because our last term is negative, and we know it has to be negative because, right, m squared has to be a positive number. And there's no way for m squared to be negative unless we're talking about imaginary numbers. Okay, so we have a positive, so we follow through. So we end up with knowing our solution is going to look something like this guy here. Okay, Bessel I and Bessel K. So if somehow you're entering something, say in Maple, that has a minus over here, and you end up getting Bessel J and Bessel Y as your answer, then you know there's some misunderstanding of the software of what you're trying to tell it to do. Right? You should be getting this equation over here, at least for this problem that we're doing. Okay, so we go through and we kind of do our bookkeeping on this and get this solution, and then our job is to so our job is to kind of assign the things and then take actions on the Bessel function. So let's talk a little bit real quickly about Bessel functions. It's not something you've really seen before. So this is a table of Bessel functions and their properties. First, let's look at what a Bessel function actually is. Let me just look down here. So if we look at what a Bessel function actually is, it's kind of this like messy polynomial series type function. And so rather than writing out the messy function every single time, some people have just given names to these sets of functions, and they have certain coefficients that go with them. Depending on the values of the coefficients, it's Bessel function of the first kind or Bessel function of the second kind or whatever. So we're dealing with these functions, Bessel K, Bessel J, Bessel Y, Bessel I. The first thing is to get their name. So Bessel function of the first kind is denoted with J, right? So you see Bessel J. And then you see this thing 0, right? 0, 1, or 2. That's the order. Right? 0, 1, or 2 is the order of the Bessel function. So when you're typing in the function in, say, ease or anywhere else, you might have to write something like Bessel J, and then the order, which is n, and then the argument, which for this is m times x. Okay, so these are just the different ways of writing them. So we have Bessel function of the first kind. It looks kind of like this. It's a decaying sinusoidal series. Bessel function of the second kind, which is denoted by y, is similar, but just a kind of shifted approach to the problem. And then you have these things called modified Bessel functions. So modified are I and k. Don't ask me why they call them modified versus regular, or why the letters are the way they are. It's just, I don't know, somebody came up with that and thought it was good. So modified Bessel function of the first kind looks like this, right? This one over here, this one over here, and then this is the second one over here. So some things to point out, right? The behavior of these are very different. Here we have an oscillating, sort of a permanently oscillating but decaying series. And then over here, we have something that looks more like an exponential or 1 over an exponential. So they behave very differently. So if your solution is trying to use Bessel Y and Bessel J, but it should be using I or K, you actually are fundamentally very different behavior that it's trying to model. Okay. Okay, these are Bessel functions. Don't need to belabor this too much, but let's see back out. So this table up here is supposed to just show you some common operations that you might do, derivatives of Bessel functions and things. So if you were, given something on an exam that needed Bessel functions and you had to take the derivative, you just come to this table, find the right function, look at the derivative. And it's not like something you should really know offhand, right? Like you remember Bessel K switches sign, but Bessel I doesn't. Like this, you just go to a table right, like this. So that's just a resource for you. Okay. So let's see, we've got our Bessel functions for this solution. Then the next thing we want to do is actually apply it. Right? I'm not writing it out because we kind of save some time here. All right, so we went with our solution from before, and we came up with Bessel I and Bessel K. So this is the solution to that ODE that we wrote before, based on what I just showed you with the Bessel functions. Okay, so we have Bessel I and Bessel K of the 0th order, and the argument is m times r. You get that from what we just did. Okay, then our job is to go through, we have unknown constants C1 and C2, and then we need to solve for those constants using our boundary conditions. So we've done this, a bunch of times now. We don't really need to spend that much time on it, but we'll just say, all right, TR equals R in is equal to TB. This is our given boundary condition here. So we plug in TB here, R equals R in here and here, as we've done right over here, right? And that helps us solve one equation. And then we have dt dr here. So we would do the differential of this equation using that table above. And we get this expression here. And so now we have two equations, two unknowns. We can solve for our constants. Or you could do this pretty easily in Maple. Just type in these boundary conditions and evaluate them in Maple. I've done that in this example down here. I don't know if we need to look at it right now, but it's there if you want to see how to do it in the lecture folder. Okay, so again, the point of fin is to transfer heat out of the system, and so we want to calculate our heat transfer rate out. We'll evaluate Q dot fin at the base of the fin using conduction, as we did before. So we say Fourier's law at the base of the fin at R equals R in here. We plug in our function for temperature. We evaluate the derivative, and we get back Q dot fin here, and then this is our expression for eta fin. Right? So this whole thing would go into the numerator here. Okay, and that's the solution. Some things to point out. Don't get too excited that we don't see TB minus T infinity up here. They actually appear in the constants. So fin efficiency is not a function of temperature, as it always has not been a function of temperature. The other thing is, the denominator looks different here than it did before. Right? Our Q dot max looks a little different because it's corresponding to this geometry that we're trying to solve. Okay, so that wraps up that example. Again, the files are there if you want to look at it in more detail or use it for a resource on the homework. Any questions on this stuff? Yeah. Yeah, so if you're given on a test, let's see, like a graphing calculator should have them. I'll have to think about that a little bit. Probably what I would do is I'd say, I'd give you a chart like this, and you could then pick off an approximate value from the chart rather than, that's maybe one way to deal with it. But yeah, like a graphing calculator would have them. Normal calculators are just, scientific calculators probably don't have those programmed. I won't expect that you have a graphing calculator.